Joel Watts. I'm a developer at asyncio Health in Houston. We've had several talks, so you may have already heard this, but we make a clinical decision support product. It's web-based and it's all Python on the back end. So we do a lot of asynchronous I/O with Tornado and G-Event. We don't actually use async I/O at work, but that may change. So anyway, that's where I'm coming from. Today I want to talk about generally about concurrency and why you should care about it. What your options are for doing concurrency in Python in your network applications, and then also like why async I/O. And I'm going to be careful because so there's async I/O, the module that was introduced in Python 3.4, and I'm going to talk about that. But there's also just asynchronous I/O more generally, and since the names conflict, I'll try to be precise. But so initially I'll be talking about asynchronous I/O, and then I will finish up talking about async I/O. And so when I talk about concurrency, what I mean is just generally doing more than one thing at a time. In the context of network applications specifically, I care about doing something useful while I'm waiting on something else to happen. So that may be a network request or a database or anything that I'm not doing myself. We're going to talk about kind of two different kinds of concurrency, or your application can be bound in two different ways, or more than two ways really. But there's CPU bound applications where you're waiting. Your CPU is what's blocking you from doing more work, and so trying to do more things if your CPU bound isn't really going to help because you're already doing everything you can. But then there also could be I/O bound, and yes, think about CPU bound as like you're waiting on yourself. And I/O bound is that you're waiting on the network or whatever, and so you're waiting on somebody else. And implemented improperly, you can be an I/O bound application that's just sitting there doing nothing most of the time. And so that's what network applications do. They wait a lot. That's my joke there. They wait a lot. So. This is a quote from Samantha. She's a character in the movie Her. It's a good movie. If you haven't seen it, you should check it out. She's an operating system. And she's an AI-based operating system. And she says this when she's describing the way it's her experience of interacting with us or with human users. And I think it's helpful when you're writing programs to think about things kind of from the computer's perspective, because it's different than your perspective. And so I'll leave that up there for a second. And then I found this table it was actually in a blog post, the same blog by Jeff Atwood on his Coding Horror blog, and it's the same post that introduced me to the Samantha quote. But what this is a set of computer latency times that are kind of translated to a human timescale. And it's difficult for us to think about really large numbers or really small numbers and compare them meaningfully, because they're not within our frame of experience generally. And so what we've done here is we've equated 0.3 nanoseconds is what we're calling a CPU clock cycle. So that's an approximation for how fast a computer does anything. And if we call that a second, so pretend you're a CPU and 1 second is your clock cycle, then we can start making meaningful comparisons about how long different operations take. And so if one CPU cycle takes a second, 120 nanoseconds still sounds really fast, but to a CPU, that's 6 minutes. And then when you start going to disk, go to a spinning platter, that's 12 months. Go to Australia, that's 20 years. So you do blocking I/O on a network call to Australia, your computer is sitting there doing nothing for 20 years. Okay. And then I had to add this to my talk today because I was in line at lunch talking to Eloy, who's in the audience. And he pointed out that we were standing in an asynchronous network application. And I thought that was kind of cool. So we took this picture. So the event loop is kind of sitting at the middle of it. And this is true. So I'm talking here about async network applications generally. So this is pretty much true of G-Event, Tornado, probably Twisted. I'll say this later, but I don't really have any experience with Twisted. So I want to acknowledge that it exists, but I'm not going to say much about it. I have more experience with Tornado and G-Event. But so you have your event loop kind of at the center of it all. And an event loop, if you're not familiar, is basically just a while true that is the main body of your program. And it's going to say, say that I'm interested in a socket, and it's going to tell the OS, hey, if anything happens on this socket, wake me up and tell me, and I'll dispatch it to my workers. And so that's what the event loop is doing here. It's the person taking the orders. They're not preparing food. They're not doing anything else. All they're doing is taking orders. And so as fast as they can take orders, they do it. And that's not entirely true. I actually saw them stop a couple times, but that's the idea, right? And so as the requests come in, they're processed in one thread, right? And then so I guess it's probably multiprocessing. The executor there is actually doing the preparation. It hands it off. And futures is another concept that we need to understand. The futures are a kind of a representation of work that is scheduled but not necessarily finished yet. And so an asynchronous call can return a future, and it's a handle that the caller can look at and say, you can attach a callback to it, or you can say, wake me up when this value is available. And so those futures are waiting for the result to happen, and then you have the people in the background, obviously, who have got their food and they're eating. So that is an async network application. So today, your options, like I said, I'm not really going to talk about Twisted much, but it's kind of the granddaddy of them all, and I felt like I needed to acknowledge it. So Tornado is the one that I've worked with the most. And let's see. I come from kind of a web development background, and so I went looking for something besides Django because I needed to do things like WebSockets and HTTP streaming and server-sent events. And I landed on Tornado, and I really like it, but at the same time, it's weird to be working with things like event loops and callbacks, and it doesn't really feel like Python. Like it actually, as a web developer, it feels more like JavaScript, because I'm setting timeouts for future things. Now, JavaScript doesn't expose the event loop explicitly, but it's there. You can see it with your set timeouts and all those things. And so that's kind of the Tornado lets you do very cool things, and but if I wanted to write JavaScript, I could write Node or something else. And I should probably say, for completeness, that Tornado, modern idiomatic Tornado, is moving towards a coroutine system that's more like async IO, and so a lot of the callbacks are going away. But and then so gEvent is kind of the other end of the spectrum that I've worked with, and gEvent is very cool. Like it takes your code looks like synchronous code, but it runs asynchronously, and it's very neat. But the downside of that is that your code looks like looks like synchronous code, but it runs asynchronously, right? Like you don't know necessarily when your code is going to switch contexts. Did that object attribute, is that actually a property that hit the database? Congratulations, you're now another greenlet. And greenlets are kind of another word for coroutines. That's generalization, but which are generators. I should probably explain that too. So generators, Python, they use the yield statement. So coroutines are kind of a lightweight cooperative threading system that's implemented. It's all in one OS thread, but they cooperate and yield between each other. And that's kind of the heart of async IO, and it's also available in Tornado, and gEvent is coroutines, really, but often it's implicitly done, and that doesn't feel very Pythonic to me. So async IO is sort of the solution to, or the attempt at a solution to the mini standards, or we have gEvent and Tornado and Twisted silos and other silos. I'm building a database driver for gEvent. Well, that sucks if I'm a Tornado developer, and I could use that async driver, but I can't because I don't have the same event loop as you. And so one of the big things that async IO wants to solve is if you can fix the IO loop problem or the event loop problem, a lot of the other problems are just kind of window dressing. Like if you have a compatibility layer in each framework, and Tornado already ships with one, then as long as you either support the standard, replace your run loop with the async IO run loop, or you provide a compatibility layer for your run loop so that other async IO applications can speak to it, then we can all get along. So that's kind of why async IO. And now I'm going to doing okay on time, actually. So I have some code examples, and this is always kind of treacherous, but I'm going to try to show code. So this is is this big enough? I can't, it's kind of hard for me to tell what's readable. Eli says it's good. Okay, so this is a synchronous server. This is all Python 3 code. So this is like a simple HTTP server in Python 2, but it's called http.server in Python 3. And so yes, I'm going to do a short sync example before I get on to async. So this is our main method. We create a server. We pass it a handler. I realize you'd probably be using Django or Flask or something, but this was less code for this purpose. So we start the server and we pass off to a handler. And so every request will get passed to a handler. And in our handler, we just supported get here. This is simple. We have a function called do something expensive. And as you can probably guess, I cheated and it just sleeps. But that's actually kind of costly. And we return howdy because we're at A&M. So how do I go back? So our function does the work. And you can imagine that this is, doing some math or converting an image, or maybe it's fetching a URL and caching it, and any number of things it could be doing that takes some time. And we do a little bit of HTTP bookkeeping, and then we write out our response. So I want to show you, and this is where it could get bad, but I'm going to run. It's not all. Actually, I can make this bigger too. But this window isn't all that important. So we will curl the request, and we get our response back. You saw a little bit of a delay. And then I'm going to do some Apache benchmark A/B tests and just kind of show. So I'm going to do one. This is Apache benchmark is A/B, -C is number of concurrent requests, N is the number of total requests, and then the URL I'm hitting. And then to cut out some of the noise I'm grepping out, I'm going to leave it in for now. But so we're doing 10 requests from one client. And so they're concurrent, or sorry, they're synchronous, so we expect that to take 10 seconds, and it does, up at the top. Can you see that up there? Time taken for tests. I'll grep it out in the future. But and so that's the problem that you see with synchronous code, though, is that if we increase the number of the amount of concurrency, so now we have 2 clients, and I'll grep time. We get the same result because no matter how many clients they're making the requests, our server can only return 1 response per second, period, because it's blocked by that function. And so this is the kind of the problem that we're trying to solve. And in the example with the food truck, this is more like a hot dog stand, right, with one guy. He's standing back there, and he's taking the orders and he's making the hot dogs. So you're not going to get him any faster than he can make them. So now we're going to go to the async IO version, and this is async IO, the module. It's also asynchronous IO, but so I'm going to hide this. I wrote a log function to, maybe I'm not going to hide it there, but it's not particularly interesting. Just makes it look the same as the other one. So we import async IO. I hope that's up there, but that's the top import if it's not. We're also calling out to there's a library called AO HTTP. So async IO, the package doesn't include protocol implementations. So like it knows how to talk to TCP sockets, but it doesn't necessarily know how to speak HTTP. So you import those, but they're fairly lightweight. And then we create our event loop in the main method here. We create a server with our handler that we defined above, and I'll talk about. Bind it to a port, and then this is where it starts to get a little different. So create server returns a future, the request future, but it represents work that is requested but not necessarily yet done. And that work in this case is binding sockets and setting up so that the OS can call back to you when network activity occurs. And the loop.rundownTellComplete is kind of a way. It's almost like turning futures around. So we take an async call and we turn it into a synchronous call. And so our run loop will advance until everything is ready to go, because our program can't do anything useful until we have the sockets bound. And then we just tell it to run forever, which does what it says on the tin. And then as requests come in, they come to our work handler above. And it's basically the same function as before. We call work.doSomething, we do some HTTP bookkeeping, we log the request, and which we didn't have to do before, but it's kind of implied. And then we get to yield from response.writeEOF. So writeEOF is a coroutine. So that's one of those suspendable asynchronous functions. And response is actually an object from AO HTTP, but it just basically wraps a network, a send to a socket and a flush. I think they call it a drain in async IO, but to me, and so write EOF is just telling the client that we are done, disconnect. And so yield from sort of tells the run loop to run that code, pause me, run that code, and wake me up when it's done, and yields the results out to your caller. It's actually a way to delegate it in. You can also use this in a generator. If you write a generator and you need to yield values from another generator, if you've ever done this, you have to write these annoying little loops where you say, for value in generator yield value. And you can now say with yield from sub-generator instead. But you can also use this to write, in async IO, this is used to do coroutines. So these lightweight threads, basically. And so we'll go back to our example. And so we're async now. I'm going to skip the single AB dash, or the single concurrency one and go to 2 and run it. So we have 2 clients, so we're now expecting it to take 5 seconds instead of 10. Ooh, that's no good. All right, so I fell into a common trap with async IO here. So let me fix that. So with async IO, it's really easy to mess it up by blocking when you didn't mean to. So my work.doSomethingExpensive function calls time.sleep, and if you call time.sleep, no amount of async magic can help you because your thread is blocked. Unless you're using gevent and they monkey patched it, but so we had to do a little bit of work here to refactor this. So I'm going to go to my work async, and so async IO provides a sleep function. And if you think I'm cheating here, I'll kind of explain why this is okay later. But so this is representing an IO bound call. So this doesn't help you if you need to crunch numbers or convert images, but if you need to make a network request, this kind of code is great. So pretend that I'm yielding from a HTTP request, if that helps. But so instead of time.sleep blocking everything, async IO.sleep just blocks the current coroutine. So my coroutine will sleep, and after a second it'll wake up and continue. So we will run this. Sorry if you're getting dizzy. And now I hope we will see that it will take 5 seconds instead of 10. There we go. And the other cool thing that I will show real fast is that this scales very nicely. And so if we do a concurrency of 10 and a connection level of 10, this should take 1 second. There it goes. And just, yeah, I'd take my word for it that it doesn't work on the synchronous server. It starts to get very long when you do it that way, but. Okay, so like I was saying, this is a reasonable approach of dealing with IO-bound asynchronous problems. So you have like a network request, but say you want to convert an image or do something expensive. So when I was preparing this talk, I thought I was going to punt like this and just tell you that the solution to your CPU-bound problem was to write a separate server that did blocking IO that you could make calls to. But then I looked more into async IO, and it actually provides some really good tools for dealing with these kind of problems, and so I'm going to talk about those two quickly. So it actually wraps the concurrent.futures module and provides this event loops have a run and executor function, which by default it runs in a thread pool. But you don't have to do any work to set it up. You just send a synchronous function to the thread pool, and you yield from it, and on the other end you get the result back. And it's very simple. And so this is actually importing our synchronous work function, running it in a thread pool, and then it'll return the result. And so we'll call in our server that uses the executor So this is actually, oh, it's already up at the top. This line that's highlighted is actually the only line that needs to, am I in the wrong one here? Oh, right. So we say from .import work async executor as work async instead of importing the other work async. So that's actually the only change in the code. And now we're running in a thread pool instead of using a coroutine. There's actually a coroutine wrapping the thread pool, but this line doesn't change. But now we're using threads instead of coroutines. And so we can do that. Where am I? All right, so we'll do 2. We're expecting 5 seconds. What am I doing? Got 5 seconds. Now, I'm not sure exactly what the numbers are, but I do want to show that when you get to the threads, and it'll be true of the process pool as well, you don't get quite the same performance in terms of concurrency because like the food truck, so it took 2 seconds instead of, so it took 1 second with coroutines, it took 2 with threads. And that's because I don't actually know how many threads it's spinning up by default, but it's fewer than 10, right? So that looks like we're around 5 threads that we probably have that we're passing requests off to do work. And so we're still limited, but this, if you're CPU bound, there's a practical limit to how much work you can do. So that's okay. And then, yeah, sure.
You had 2 examples that you just did. One, you had to use a specific async IO sleep call, and the other one, I think for the threading example, you called out and did the normal work function, which was just the call to sleep.
This here, yes.
Yeah.
So, but yes, so here I'm calling time.sleep, and the other one I was calling async IO.sleep. Is that?
Okay, so I guess my question is, if I had to do something like, if I was using the request library to go out and grab some data,
Okay.
and it was taking a while, that's not I guess the confusion comes from you had to use the async IO.sleep.
Sure.
And so I'm just wondering if one method lends itself to things that kind of have to be async IO aware, whereas the other one lends itself to just kind of being able to do whatever you want.
So I think a good way of thinking about it is that so you can probably do any use case you have, you could pass off to it's probably not any, but to a thread pool or to a process pool, and it would be fine. There are a case of problems like HTTP requests that you can do even more efficiently by using the coroutine method. And it's basically boils down to if somebody else is doing the hard work and you're just waiting on them to get done, then you're better off doing it in the coroutine and just waking up when they're done. But if you need to do work on your own CPU, then you can hand it off to the thread pool or the process pool. Process pool probably better if you're talking about CPU stuff. But if you're talking about network lookups and that kind of stuff, the thread pool is good. Does that kind of answer your question? Yeah, I think work that you're doing yourself, think process threads. Work that somebody else is doing, think coroutines. Depending on who you're waiting on. And then real quick, I want to show this is going to be, I'm going to change from a thread pool to a process pool. And my work, I do something expensive function doesn't change. And I need to type server here. And the only thing I have to do to change to a process pool is I import concurrent.futures. And then here at the bottom, in my main method, if I can find my cursor, I'm lost. Here we go. We create a process pool, which is just a pool of, by default it creates a pool with the number of workers that matches your number of CPUs or number of cores. So this is dual core, so I have two workers. And then you tell the loop to use that executor instead of its default executor. And then you're using processes instead of threads. And I'll run it, but it works exactly the same way. Should get a 5 and I think it's 2. I ran this earlier and got 3, so I'm not actually sure what's going on there, but I guess there's just a little bit of overhead anyway, and that's kind of all I've got. So async IO provides these wrappers for, do IO-bound concurrency in coroutines. You can do CPU-bound concurrency in thread pools or process pools, and it all provides a common interface that allows you to wait on those results and proceed. Oh, and I guess I did want to say with this line, kind of the magic that this is sort of bringing it all together, that yield from, so yeah, that's, you don't write yield from usually, but that looks a lot like the line that just says text equals work dot do something expensive. So I think that's very close to the G-event style of almost looking synchronous, but at least it has the syntactic, it has the benefit of telling you that asynchrony is happening. So I think that's kind of the best of both worlds, and I really like how that works, sorry. So I think I've got no time, but I'll answer questions as long as they let you ask them.